Let me show you some steps that we can follow to find dy dx if we're starting with an implicitly defined equation. So on the right-hand side, you can see an example of an implicitly defined function, x squared plus y squared equals 1. And the question is, what is dy dx? So on the left, I'll write the general steps, and on the right, I'll work through them in the example. Step 1 is just something to remember. We're going to remember that we're treating y as a function of x. So if x is the input, y is the output. So there's nothing to write down, nothing to do really here. Step 2, this is an equation, meaning the left-hand side is equal to the right-hand side. We can do the same thing to both sides, including taking a derivative, and the equality will still hold. So we'll take we'll take d dx, the derivative of both sides with respect to x. And when you're applying this step, don't forget that since we're treating y as a function, it might sometimes be the inside function for applying the chain rule. So back to our example, we'll take the derivative of the left-hand side and set that equal to the derivative of the right-hand side. On the left, derivative of x squared 2x, the power rule. The derivative of y squared, also the power rule, 2 times y. But then we need to multiply by the derivative of the inside function. The derivative of y is dy dx. And on the right-hand side, well, the derivative of 1 is just 0. 1 is a constant. So step 3, if the question asks us to solve for the derivative at a particular point, then now is when we would plug in x and y values if we had them. In this example, we don't. We'll see an example where we do later. And step 4, solve for dy dx. The question is, what is dy dx? So let's solve that. We'll get that quantity alone on one side of the equation. So we can subtract 2x from both sides. We can divide both sides by 2y. And after canceling the 2's, we see dy dx is minus x over y. So what does that tell us? That tells us that any point on the curve given by x squared plus y squared equals 1, the change in y over the change in x is given by this value minus x over y. So it depends on the x value as well as on the y value. In this example, we'll consider this implicitly defined function given by the equation x squared plus xy minus y squared equals 4. And the question is, what's y prime? So step 1, remember that we're treating y as a function of x. So nothing to write, just something to remember, to think about. And when we say y prime, we mean dy dx. You can write either one if it helps to remember. Really, we're asking about how y changes as x changes. So the first step, we'll write down this equation and we'll take the derivative with respect to x of both sides. So using the power rule, the derivative of x squared is 2x. xy, the derivative of that is x times y prime plus 1 times y. And the derivative of y squared is 2y y prime. So that xy prime plus 1y, that comes from using the power rule. And the 2y y prime, that comes from using the chain rule. Remember, y is a function, so when we apply the product rule, when we apply the power rule, as we did, we can't forget to multiply by the derivative of the inside function, that is the derivative of y. And of course, on the right-hand side, the derivative of 4 is just 0. So there are no values to plug into here. Our next goal is to solve for y prime. So we'll take all the terms that don't involve a y prime and we will move them over to the right-hand side. And now to get the y prime out of these terms on the left, we can factor. We can factor y prime out. And then we'll divide by that factor to isolate the y prime. And this is the expression we get. So we'll take a look at a picture of this graph so you can see what's happening here. But what this is telling us is if we find any point xy that's on the curve defined by this implicitly defined function, the rate of change would be given by this function. In other words, if we were to draw a tangent line, the slope of that tangent line would be given by this function. So let's see an example. Here, we're looking at a plot given by this implicitly defined function. X squared plus xy minus y squared equals 4. So this isn't something we can type into our TI-83 graphing calculator, but and it's certainly not a function. This graph doesn't pass the vertical line test, but there is a collection of points xy that make this equation true. And what we're looking at is that collection of points. So every point on these two curves gives a solution to those. For example, let's find a nice one. So -2, -2. So you can check that if you plug in -2 for x and -2 for y, then this equation is true. So what we just found was an expression for the slope of a tangent line at any point. Well, you can see, for example, there are 2 points on this curve where the x value is -2. And the tangent lines will have drastically different slopes. One of them will be a negative slope up here at the point -2, 0, and the other will have a positive slope down here at the point -2, -2. So knowing the x value isn't enough to talk about the slope of the tangent line. We also need to know the y value. And that was baked into this expression we just found for dy dx. So you can check it out, maybe play around with this, graph this in GeoGebra, draw a tangent line, and you'll see the slopes of the tangent lines should match exactly that function we just found if you plug in the corresponding x and y values. One last example. So this funky blue curve that we see, it's the set of the solutions to this equation, x squared plus y squared equals this quantity 2x squared plus 2y squared minus x, the whole thing squared. There's a point on it, 0, 1/2. If you're really interested, you can check that that point, those x and y values satisfy this equation. But through that point, we can draw a tangent line. Now, this is not a function, not an explicitly defined function. It doesn't pass the vertical line test. We couldn't write it in the form y equals. But we can still ask about the slope of the tangent line or the equation of the tangent line. And that's exactly what I want to do here. I want to know what's the equation of that tangent line. So to start, remember that we're treating y as a function of x. When we talk about slope, we want to know how does y depend on x? Or more specifically, how does y change as x changes? So to talk about the equation of the tangent line, we need the slope, that is dy dx. So we'll take the derivative of both sides of this equation. I know this looks bad, but bear with me. The left-hand side, well, we've already done something that looks just like this. So the derivative there, 2x plus 2y times dy dx. And on the right-hand side, we need to use the chain rule. So we'll use the power rule. This whole expression is raised to the second power. So we'll bring the 2 out to the front. We've got 2 times that quantity on the inside. The power becomes 1. We don't need to write that. And then, as the chain rule dictates, we need to include the derivative of that whole inside expression. And we can do it as long as we're careful. We'll use the power rule for all 3 of these terms. We'll remember 2y squared is a function of y, which itself is a function of x. So we can't forget to use the chain rule and multiply by dy dx when we do that. And now, if we had to solve for dy dx at this point, it would be a royal pain. But luckily, we are only interested in dy dx at a particular point. So let's plug in the x and y values for that point. So we'll do that here carefully. Dy dx is still a variable. That's the thing we don't know that we want to solve for. So that hangs out. But every x will replace with 0, every y with 1/2. And after simplifying a little bit, we get this really nice expression, dy dx equals 1 times 2y dy dx minus 1. So we can subtract dy dx from both sides. We can divide by minus 1. And we see dy dx is 1. So all that work ends with a pretty nice answer. Dy dx is 1. We're not done yet, but we're almost done. We need the equation of the tangent line. So we found the slope is 1. We know the point 0, 1/2 is on that line. We can plug it in using point slope form, and you're welcome to leave your answer just like that. Or we can add 1/2 to both sides and put it into slope intercept form. And if you look at the graph again, I think you would agree that this is the correct answer. Nice job.